All right. This part is just going to be going through. So it's kind of like the key tools that you're learning from this course to do with concepts around melting, magma differentiation, all that kind of thing, and then some of the things like major trace elements, phase diagrams that we've been relying on. Okay. So to Oscar's dismay, we're starting with magma differentiation, crystallization, and phase diagrams. So starting off really broad, the concept of differentiation is just this idea that as we melt the mantle and magmas crystallize and evolve, or even as we melt the crust, we are gradually producing more and more felsic compositions from a starting point of ultramafic mantle. And differentiation can be even more broad than this. Like you can talk about differentiation of whatever Earth was originally into a core and a silicate, but it's basically this process of separating out different minerals. In terms of magmas and volcanism, it's usually this process of going towards more and more felsic compositions through magmatic processes. So different differentiation processes drives the wide diversity of igneous rocks we see on Earth. So if we melt the mantle, which is ultramafic, we generally get mafic compositions like basalt. If we melt existing crust, so whether that's kind of mafic, igneous crust, then we'll get something like a tonalite, which is a granitoid. If we melt something like a sediment or a more evolved igneous rock, then we'll get something like a granite. Differences in melting styles, so difference between dry adiabatic decompression melting or flux melting can also cause differences in the differentiation paths that we see. How much fractional crystallization, assimilation, and all these other processes also drive different amounts of differentiation. So a very, very primitive melt tends to be quite a mafic composition, and the more fractional crystallization or crystal assimilation we get driven to more felsic compositions. Okay. Being a bit more specific than that, incongruent melting is one of the key drivers of differentiation, and that is because most melting is non-modal. So different minerals contribute different amounts to the melt, and this means that the melt has a different composition to the source. There's just a simple phase diagram that I showed in the very first lecture, and the corners are forsterite, so olivine, enstatite, which is the magnesium-rich orthoperoxine, and diopside. And you can see that if we start with a lertzolitic mantle, this is our kind of fertile mantle peritite, and we melt it, then the melt composition is much closer to the diopside corner. So it is less ultramafic, there's less olivine in that composition, and it's much closer to a clinoperoxine composition. So yeah, basically producing a basalt, a mafic composition from something ultramafic. Similar thing happens as magmas crystallize, and that's because the crystals, again, don't have the same composition as the magma. So in general, as we crystallize a mineral, we move the magma composition away from that because we're taking that out of the magma, and magmas become more and more evolved with crystallization. So again, generally going towards cooler, more felsic compositions. And this is a diagram showing that. 1200 degrees, it's something like a basalt, it's probably just crystallizing olivine, then maybe clinoperoxine, plagioclase, and some other stuff, and then we end up with a relatively cool melt that is much more felsic, and a bunch of crystals that form from it. We talked about this specifically to do with trace elements, but the kind of overall concept applies to everything. We have these two different models of how crystallization can happen. The first one is equilibrium crystallization, and in equilibrium crystallization, everything's in equilibrium. So this means that the crystals form from the magma with one composition, but as the temperature cools and more of that crystal grows, then the composition of the crystals is adjusting to stay in equilibrium for the magma. So the implication of this is that we can't have any zoning and that the crystals have to remain in contact with the evolving magma. Now, this is the style of crystallization that all the phase diagrams use because they're based on melting experiments where people try and heat everything to the same temperature and sit it there until it's all equilibrated, and then they measure, how much olivine do I have, how much melt do I have, all that kind of thing. Fractional crystallization is the much more realistic one in nature. And what happens is, as the crystals are crystallizing, they are in equilibrium at that instant with the magma composition. But then as crystallization continues, those kind of early crystallized compositions are basically shielded from the magma by new growths of mineral around the edges. The other way we can get this kind of isolation of the early formed crystals is if they sink from the magma to make a cumulate, and then they're no longer in contact with it. So for fractional crystallization, the crystal composition should be constant after it forms, and we basically just grow new zones, or we dump it out and then we grow new layers of cumulate. So this is much more realistic for a lot of crystallization, but it's very hard to replicate in experiments, which is why we use the equilibrium crystallization for the phase diagrams. We have basically the same concept for melting. We can either have fractional melting or batch melting, and batch is just equilibrium melting. Again, for the equilibrium melt, the melt remains in contact or in equilibrium with the solid as melting progresses. So you can see it here. If we start with a solid source that has one composition, and this is kind of a medium gray, when we make the melt, which is black, we're left with a source that is a light gray, but they're sat there together in contact. For fractional melting, as soon as you form a little increment of melt, it is removed. That could be because it's buoyant and it flows upwards. And so you're left with a residual solid plus some amount of accumulated or not accumulated melt. So all these little increments, they can either get to the surface quite quickly as little incremental melt fractions, or they can mix somewhere in a magma chamber or a channel or something. Catherine, you had a question?
In which cases or scenarios would you see batch melting in practice?
So granites would be a really, because we talked about in the granitoid lecture that they're incredibly viscous, and so they don't get removed from their sources very well. So if we do dehydration melting in muscovite, usually the melt fraction is not high enough for it to flow. So it's basically going to be batch melting, because you'll have that melt sat there in between its residue like a migmatite. And so that is exactly this scenario. And only once we get to very, very high degrees of melting can the melt actually leave. So in a granite, you might have, say, 30% batch melting, and then it will be one of these dynamic or critical melting scenarios where our threshold for removing melt might be 30%, and it actually leaves. But then if melting continues, it'll carry on accumulating melt in between until it hits that threshold again, and then it can leave. So it'll be much more similar to batch melting. So yeah, this critical melting is kind of in between. This is what we think happens in the mantle, and it's because basaltic melts they're low viscosity, they can flow very easily, everything's at high temperature, and so you probably get melting up to about 1% or so, and then any melting past that, the melt is able to move out. But it's never able to fully kind of squeeze out every last drop of melt. So there's a little bit left behind. And so this critical melting, dynamic melting, is a bit like little steps of batch melting with fractional melt removal once you hit this threshold. All right, phase diagrams. So phase diagrams, and I've tried to give like a bit more background in this than I did in the lectures, but they're basically ways of summarizing experimental results. So people have gone out, they've basically taken a bunch of rock compositions and melted them, and then they've plotted out, at what temperature do we first find a melt? At what composition do we start to see two things crystallizing instead of one? And once these results are summarized, we can basically look at them to see what crystallizes or what is stable at different conditions. So when I talk about what is stable, I mean it's not just minerals. There's also the liquid melts, and then also these can be used for stuff like fluids, right? We talked about there was a phase diagram of water, and we had some sort of threshold pressure curve with water, and when we hit that, then we start to make a gas. So it's not forming a crystal, it's actually making bubbles instead. And they vary, you can vary the conditions. For example, these are all shown against temperature. So the top one is temperature against the composition of olivine. And the bottom one is a ternary phase diagram where we can see the which of these minerals, A, B, or C, is crystallizing at a given composition. And we can see the temperature at which they start to crystallize. So yeah, we can use them to kind of describe or in some cases predict how magmas are going to behave depending on their composition and the conditions. So binary diagrams can be all sorts. You can have pressure temperature binaries. You can have a temperature versus composition, which is usually called X. So this top one up here would be a TX, or a temperature composition diagram. And then the ternary ones are almost always 3 different chemical components at the corners of the ternary, and they're usually against temperature, just because these are mainly used for magma crystallization. And the important thing to remember with the ternaries is you can't always see these contours, but they are implied, and they're usually implied by the direction of the arrows, right? So we're always going down temperature. So if you see arrows coming into this central point here, then we know that we must be flowing downhill from the corners into the middle. Okay. So Gibbs phase rule, really simple to remember. F equals C minus P plus 1. F is the number of degrees of freedom, and these are parameters like temperature, pressure, and composition. C is the number of chemical components, and these are just the compositional end members. And P is the number of phases. And what this means, and this is just showing a forsterite quartz binary phase diagram, and it's plotted as a function of temperature, is that we can basically tell how many phases they're going to be crystallizing at a given point, or we can tell whether we have whether we're evolving along a line in temperature, or whether it's staying at constant temperature, or whether we have this big field of variable temperatures and compositions. So the example here, we have 2 components, and that means that if we only have one phase, a liquid, then we have 2 minus 1 plus 1 is 2. And that means that just a liquid on its own can exist as a field at a range of temperatures and a range of compositions. If we have forsterite plus liquid, then because we have 2 phases, we have a liquid, we have forsterite, then we only have 1 degree of freedom. And that means that if I tell you the temperature, then you can tell me exactly what amount of forsterite is there. We can't freely choose. And so when we hit these lines, basically the liquid is moving down this composition as we crystallize forsterite. At something like the eutectic point here, which is we have enstatite, cristobalite, and liquid, we have 0 degrees of freedom. So it only exists at a single temperature, and it's only exists at a single composition. So you can't move it, there's no freedom. Same with this peritectic point here that we'll talk about afterwards. Okay, the lever rule, and obviously we covered this in phase diagrams, but this applies to geochemical diagrams, major and trace element geochemistry. It's just a very simple way of thinking about things, and once you get used to it, you can kind of just look at a diagram and be like, it's about 70% of this and 30% of that. So this is the formula for it, where if we want to find out the percentage of the mineral D that's crystallizing at the solidus, then we just do X minus C, so this is this distance, divided by this distance, and then times by 100 to get percent. So you can think about it as this kind of lever or balance. The closer you are to one end, the more of it you have. Okay, so if the composition X was over here, then we have 100% of crystal at D, and we have no melt. If the composition X was over here, then we have 100% melt, and we have nothing crystallized yet. And so obviously, as the temperature changes, the proportions of the melt and the crystals will change for a given bulk composition. All right. So this move on to how we can use phase diagrams in understanding magma evolution. So first, this is a binary phase diagram, and it's for plagioclase plotted as a function of temperature. And so what we can use this for is we can kind of predict what kind of composition of plagioclase we're going to crystallize from a given melt composition. And we can also use it to understand how the composition of plagioclases evolves with ongoing crystallization. So here, if we start with a melt composition here and we just cool it, eventually we hit the liquidus. So above the liquidus, we only have melt. At the liquidus, this is the temperature, the lowest temperature at which it's completely molten. And the plagioclase composition that is in equilibrium with this liquid is over here at the solidus. So we can see that for this, which is a liquid with 36% anorthite and 64% albite, the first plagioclase to crystallize has 71% anorthite. As we cool, the liquid composition moves down this way. And it's because we're going down in temperature, but we're also crystallizing out this anorthite-rich plagioclase. So the liquid has less and less anorthite left, and it gets more and more albite-rich, gets more sodium-rich. And so at this temperature, the liquid has this composition, and the plagioclase, the average plagioclase composition, because it's equilibrium crystallization, so the plagioclase is going to keep adjusting to match the liquid, is going to be over here. And this carries on until we're 100% crystallized, and the reason we're 100% crystallized is the crystallizing assemblage is now the same as the average composition, so we can't have any melt left. All right. So for this composition here, we've now hit the solidus, and it's all crystallized. At every stage, you can do lever rule to see how much melt we have and how much crystals we have. So this can both help us understand, obviously, plagioclase at high temperatures, so mafic melts, we get anorthite-rich plagioclases. At low temperatures, for more felsic melts, we get albite. And the same applies to olivine, which goes from magnesium-rich forsterite at high temperatures to iron-rich fayalite at low temperatures. All right, all of that was binary diagrams, so usually we're just talking about a melt and then one phase crystallizing. And eventually we can hit a eutectic where we have 0 degrees of freedom and it's at a fixed temperature, and that is always going to be 2 minerals and a melt, because that's from our Gibbs phase rule. We then have 0 degrees of freedom exists at one temperature, one composition. For ternary diagrams, we have an extra component. So from the Gibbs phase rule, we can see we hit the liquidus, and there's usually just going to be one mineral crystallizing. Now that can exist at a range of temperatures. It can exist at a range of kind of, in this case, diopside or forsterite contents, and a range of forsterite or anorthite contents. So we have 3 degrees of freedom. What happens then is, as you're crystallizing, you move away from the composition that you're crystallizing. So if we start with this melt composition Y, we are crystallizing forsterite, which means the melt is becoming less forsterite rich, so there's just less of it left. And then eventually we hit something called a cotectic. And for this cotectic, you have 2 minerals plus liquids, so that's 3. And so we have 1 degree of freedom. So for for a given temperature, you know exactly what composition this is going to be at. And at these cotectics, we move down temperature, crystallizing our 2 minerals, and that will continue until we hit a eutectic. And a eutectic point is where we have 3 minerals crystallizing plus our liquid. So we have 0 degrees of freedom, so it is a fixed temperature and fixed composition. So in a binary phase diagram, we can only have eutectics because we don't have 3 components. So we can't have a situation where we have 2 minerals crystallizing and a melt and the temperature's changing, because there's no degrees of freedom left. Okay, so we can see here that the order in which minerals crystallized in a basalt is going to depend on the starting composition. So something like this, Y, might be something like, say, a mid-ocean ridge basalt, where you go from olivine to plagioclase, and then down to olivine, plagioclase plus clinopyroxene. Something like X here, which is a higher temperature melt, could be something like a pickrite, where we crystallize olivine first, we move away from olivine until we hit this dioxide cotectic, and we're crystallizing olivine and clinopyroxene, and then eventually we crystallize plagioclase. The last type of crystallization process that we need to talk about are peritectic reactions. And I was thinking a bit about how to explain this better because I think I butchered it the first time around. So I think the way to think about it here is if we start with a melt composition A, it starts crystallizing forsterite, and we're reducing the amount of melt as we crystallize it. And the melt composition is moving over here. What happens is at composition A, at low temperatures, we have to end up with some mix of forsterite and enstatite, right? Because we have enstatite here, we have forsterite here, so everything in this field is a mixture of forsterite and enstatite. What happens is we actually crystallize olivine until we've kind of overstepped the boundary. The melt composition has now left this field of forsterite and enstatite, and we're now in this kind of enstatite plus liquid, where you'd eventually need some combination of enstatite and cristobalite from this mineral, from this liquid composition. So to get our final solid composition back here, we actually have to react away some of the olivine that we've crystallized and replace it with orthoperoxene to move us back over here by the time everything's solid. So it's at equilibrium, so we're actually able to dissolve all this olivine that crystallize too much olivine, and then it's like, oh shit, time to dissolve the olivine, and then move back to our original average composition. Does that make a bit more sense than the first time? I hope it does. Yeah. Okay, so at these peritectic reactions, one mineral is being consumed through a reaction with a melt, or if you have more complicated systems with more components, you could potentially have a couple of minerals dissolving and a couple of minerals crystallizing. So here at this peritectic point, the reaction that's happening is forsterite plus liquid is making enstatite, and that allows our final composition to be forsterite and enstatite with the same composition we started with. This kind of reaction is both important for making norites through crustally contaminated ultramafic rocks, and also for making dunite channels in the mantle. So the dunite channels in the mantle are literally this exact reaction. We have a liquid that's coming through and reacting with the enstatite to make forsterite. Norites are a bit more complicated, and we could see that with the peritectic ternary, where you basically have olivine plus a liquid reacting to make enstatite plus plagioclase. All right. Major and trace element geochemistry. So we can broadly divide elements into major, minor, and trace. And the implication of this, they're divided based on abundance, but the implication is that major and minor elements are influencing what minerals are formed. We usually report them as weight percent oxides. And major elements, those with more than about 1 weight percent. Minor elements are between 0.1 and 1 weight percent. The compositions vary with the rock type, and I said here they reflect the mineralogy, or more like the mineralogy is reflecting the major element composition. And so you can see in something like a mantle peritite, we have fairly low silica and very, very high magnesium, and we're actually quite close to an olivine composition, which is why there's loads of olivine in a mantle peritite. As melts get more and more evolved, they tend to go higher and higher in silica and lower in magnesium. And so rhyolite, we've generally got loads of silica, a lot of aluminium, and some alkalis, so that's giving us quartz and feldspars. So the mineralogy is just reflecting that composition. Trace elements, by contrast, do not cause crystallization of new minerals. They're kind of just along for the ride. They will sit wherever they can, either in a mineral or in a melt. And they're defined as having less than 0.1 weight percent of the element, but we usually report them as parts per million. The useful thing about trace elements is because they have very low concentrations, then they follow this thing called Henry's law. They basically approximate ideal behavior, and what that means is as we increase the concentration in the melt, the concentration in the solid goes up proportionally. And so this is useful because it means we can use partition coefficients. I've just got a quick note here on calculating mineral major element weight percent from formulas, but I probably recommend you go back to the practical that we did or even the original lectures to get a better overview of this. This is the fairly simple example from olivine, and if we have a magnesium number or if we have some sort of mineral formula, then we can calculate the weight percent oxides from it. And the way this works, olivine is simple because we're just caring about the FO content or the Mg number. This is just the ratio of magnesium to iron. So if the FO content or Mg number is 89, that means we have 89 parts magnesium to every 11 parts iron. And if we put that into the olivine formula, which is MgFe2SiO4, then we basically just double this to get 1.78 Mg, 0.22 iron, and then SiO4. From that, we break it down into these different components. So we have MgO, FeO, and SiO2. And we just multiply each one by the molecular mass. So MgO, and magnesium's got a mass of about 24, oxygen's about 16, and so on for the other ones. Once this gives us the relative mass of each one, and then we just add all these up and divide by the total, and this gives us weight percent oxides as a percentage. To go from weight percent oxides to a mineral formula, we're basically just reversing the process, and then you just have to make sure, instead of it adding up to 100%, you have to make it add up to the right number of oxygens. Okay, we usually plot major element variations on these things called Harker diagrams, and this just saves you looking at these huge tables of data and not being able to read much. Typically, they're plotted against differentiation indices, so we often use MgO, magnesium, the Mg number, which is calculated in the same way as the four-strike content. It's just the molar magnesium divided by the molar magnesium plus iron, or silica. And the reason for that is that MgO is pretty much always dropping during magma differentiation, whereas silica is almost always going upwards. And what you can do with this is you can compare it to the composition of minerals or mixtures of minerals to see what's crystallizing. It also just gives you kind of a summary of, what the approximate compositions are, and you can even distinguish whether stuff can form from a single differentiation trend or whether you have two groups from different magma suites. So again, same as the phase diagrams, the melt composition moves away from whatever is crystallizing. And I hope you remember this from the mid-ocean ridge example that we did, is that early on we have some mixture of about 30% olivine and 70% plagioclase crystallizing, and so that's up here. And so the composition of the melt moves away from that. So we can basically just draw a line between our starting melt and our crystallizing composition, and we know that the melt is going to carry on along that trend away from it. Similarly, if you have three things together, this is a mixture between plagioclase up here, very high aluminium, clinoproxene down here, which is low aluminium and kind of a moderate MgO content, and olivine, which is way off the end of this diagram because it's got really high MgO and low aluminium. If we have some sort of mixture of the three minerals like this, then we crystallize and melt evolves away from that composition. These diagrams often have quite a bit of mess or scatter in them because lavas they're not pure melts. They're mixtures of melt and phenocryst, and then there's potentially other processes going on, like we might not just have a single parental melt that everything's crystallizing from. In this example, it's the whole East Pacific rise, so thousands of kilometers of mid-ocean ridge, and it actually fits pretty well to these crystallizing assemblages, but we can still see a lot of scatter in it. Okay, concept of compatibility. Now we talked about this specifically with trace elements, but it also applies to major elements. And whether an element is compatible or incompatible depends on the ionic size and charge of that element compared to this kind of ideal charge and size of a site in a mineral. So here's an example from olivine. It's got these M1 and M2 sites that are almost the same size, and they basically want 2+ cations that are, I think it was something around 0.7 angstroms. So this is 10 to the minus 10 meters. Now, the sites are different in every single mineral, and most minerals have a few different mineral sites in which ions can fit. So elements can be incompatible in some minerals, but compatible in others. For example, aluminium is very incompatible in olivine. It doesn't really fit in the tetrahedral site or these M1 or M2 sites, but it's obviously a major constituent of feldspars, so it's compatible in feldspar. For trace elements, because they follow this Henry's law, we can describe whether they're compatible or incompatible using a partition coefficient. And the partition coefficient is just the concentration in the mineral divided by the concentration in the melt. Now, the partition coefficient will change depending on the temperature or the pressure or the melt composition, but the important thing is it's independent of the trace element concentration. So that means if we double the amount of, say, strontium in a melt, the partition coefficient should be exactly the same. You'll get twice as much in the crystal as well. If the partition coefficient is high, if it's above 1, then the element is compatible in that mineral or in that crystallizing assemblage. If it is below 1, then it is incompatible. This means that it prefers to be in the melt than in the crystallizing minerals. For things that are like very much less than 1, they're described as highly incompatible. A couple of you asked before, I don't know if there's like a hard and fast boundary, but you'll just hear this term bandied around that things are highly incompatible. So if we have several minerals crystallizing, then we need to calculate a bulk partition coefficient. And this is just the partition coefficient for each of the minerals for that element multiplied by the mass fraction of that mineral within the crystallizing assemblage. So if we have something that's crystallizing 70% plagioclase and 30% olivine, then the bulk partition coefficient for a trace element like strontium would be 0.7 for plagioclase, so 70%, times the partition coefficient of strontium in plagioclase, plus 0.3 times the partition coefficient of strontium in olivine. So for these bulk ones, it's important to know that we're doing it for lots of different minerals, but there would be a different bulk partition coefficient for each element. All right. Equilibrium versus fractional crystallization from the trace element perspective. Obviously, we've gone over what the concept is, that in equilibrium we're constantly adjusting the mineral composition, and in fractional we're removing it in some way, either by isolating it with new minerals crystallizing around the edges, or by removing it physically to make a cumulate and separating it from the magma. So regardless of the style of crystallization, in both cases, if we have a compatible element, so it's got a bulk partition coefficient of more than 1, then the concentration in the melt drops as crystallization goes on, and that's because the element's being removed into the crystallizing assemblage. For an incompatible element, then because we're forming crystals but we're not putting that element into the crystals, then the concentration goes up in the melt. So if we have a very incompatible element, then it goes up quite quickly. If we have something that's a bit less compatible, then it goes up a little bit more slowly. The main difference between these two diagrams is that the changes are faster for fractional crystallization. And so if we have a highly incompatible element in fractional crystallization, it will go up more rapidly at first than in equilibrium crystallization. And the same goes for the compatible elements. For fractional crystallization, we basically remove compatible elements very, very quickly, very early in crystallization. And obviously how fast they're removed depends on how compatible they are the most compatible ones are removed the fastest, and the less compatible ones are removed slower. At the end of crystallization, we will end up with the same thing, right? Pretty much. Same thing goes for equilibrium and fractional melting. As we melt things, in either case, compatible elements get concentrated in the solids, and so they're quite low in the liquids until we get to very, very high degrees of melting. And then right at the very last stages of melting, the last melts, once we melted 100%, we have to end up with the same concentration in the liquid as we started with, because we've got to have the same average composition. So yeah, in equilibrium melting, we start off low incompatible elements, and eventually we get to the same as our starting composition. And for incompatible elements, they are highest at the smallest degrees of melting. So the very, very first melt that we form is very high in incompatible elements, and that drops as melting progresses. And that's just because as we form more and more melt, we're essentially, there's no incompatible elements left in the solid assemblage. And so the new melt that is forming is not contributing extra incompatible elements, but it's contributing more melt, so we're diluting it down. Same goes for fractional, except in the very, very last stages of fractional melting, the concentration of compatible elements gets pretty extreme. But the incompatible element behavior is pretty similar. We start off with very high concentrations in the very first melts to form, and then those drop as the melting progresses. Something you'll notice here is that in the fractional, again, the changes are more rapid and they're more extreme. So we'll eventually just completely deplete the incompatible elements from the residue. So for example here, past about 50% melting, if an element has a bulk partition coefficient of 0.1, there's nothing left. Whereas in the equilibrium one, because the melt and the residue are always staying in contact in an equilibrium, we always have some of these incompatible elements hanging around. And again, at 100% melting, the melt has the same composition as the original solid. So the changes are more extreme and they happen more rapidly during fractional melting. But broadly, higher incompatible element concentrations at the lowest degrees of melting. Okay. Some of the important groups of trace elements that we covered, we have the rare earth elements, or REEs. These are important because they have a progressive change in ionic size at a constant charge of 3+. So the important thing to remember here is that the light rare earths have the bigger ions, and so they are the most incompatible, and the heavy rare earths have smaller ionic radii, and they are the least incompatible. They're all still broadly incompatible in most, say, mafic crystallizing assemblages and during mantle melting and this kind of thing. Another key group we talked about was the high field strength elements. These are things like zirconium, hafnium, titanium, niobium, and tantalum. And these have a very high charge relative to their ionic size. They're still highly incompatible, but they're not very mobile in fluids. The large ion lithophile elements are basically the opposite. They have a very, very high ionic radius compared to their charge, and they're also highly incompatible, but these are highly fluid mobile. So they're easily removed by water and other fluids that are passing through the rock. We can plot the rare earth element data as these rare earth element patterns. They have to be normalized to either chondrite, which is our kind of meteorite that gives us an estimate of the original solar system composition, or primitive mantle, that's some sort of estimate of what the mantle composition was after core formation. This smooths out the spikiness in the patterns that we get otherwise, which just comes about from odd-numbered elements having lower abundances than even-numbered. What's great about these patterns is we get these very systematic variations due to the systematic changes in ion size that give us a change in the partition coefficient. So the light rare earths are more incompatible, and they get enriched either if we have a source that is already enriched in light rare earths. So if our source was already had a slope in this direction, or just if there's very low degrees of melting. And that's because the most incompatible elements get concentrated more at the low degrees of melting. If we have high degrees of melting, then we get progressively flatter patterns because the difference in the concentrations between these highly incompatible light rare earths and the less incompatible heavy rare earths is basically getting diluted down by adding melts that don't have as many light rare earths, just because we mostly removed them from the source. The other reason we can get kind of flat or even these sort of declining patterns is if the source is already depleted. So this is the case for mid-ocean ridge basalts. We have relatively high degrees of melting, maybe about 20%, and we have a source that is already depleted, so it's already had some of the light rare earths removed preferentially over the heavy rare earths. Alkali basalts, which tend to be much lower degrees of melting, they are enriched in light rare earths compared to the heavy rare earths. There's a couple of kind of special behaviors that you need to be aware of. Europium and cerium can be anomalous because they can actually have different oxidation states. So europium can be europium 2+ as well as 3+, and the europium 2+ version is compatible in plagioclase. So if we've crystallized and removed plagioclase from a magma, then we get a negative europium anomaly. In cumulates that have lots of plagioclase, we get a positive europium anomaly. Cerium can also be 4+, but I think that's probably more relevant to sedimentary rocks. The other special behavior is that the heavy rare earths are compatible in garnet. So if we have very deep melting, a kind of average depth of melting is in the garnet peritite field, then we will have a lower heavy rare earth compared to light rare earth ratio. And so this kind of increases the slope of these diagrams. Okay. If we extend those out to include lots of different trace elements, then we get a spider diagram or a spidergram, or all the other names for it. These are really useful for identifying subduction zone magmas, and the reason for that is because fluid in subduction zones enrich, so these fluids that are being driven off the subducting slab, they basically strip out the large iron lithophile elements plus some other elements including thorium, uranium, light rare earths, and strontium, and they can then enrich the mantle wedge in the subduction zone in these elements. The higher field strength elements are not fluid mobile, so they get left behind in the slab. And so we have this signature where we're enriched in the large iron lithophile elements, but no enrichment in the high field strength elements. And it makes this kind of spiky pattern. So subduction zone magma is going to be high in strontium, high in thorium, high in rubidium, barium, and it's going to be very low in niobium, tantalum, often titanium as well. You can also get this because most continental crust or modern continental crust originates from subduction, then we can also see this for crustal contamination. We're basically adding a subduction zone signature, but from the crust rather than from fluid behavior in the mantle. Because the rare earths and a lot of these trace elements that we plot in the spidergrams, they're incompatible in most mafic minerals, and so all that means is that when we crystallize, we're just concentrating these incompatible elements in the melt without changing the slope of the diagram. So we're not fractionating the light rare earths and the heavy rare earths, and so the whole thing just moves upwards in concentration without changing shape. However, if you do have something that's compatible, say like europium here, then you'll start to get these anomalies, as in this case plagioclase is crystallizing. Iron titanium oxide crystallizing could also create a negative titanium anomaly. Okay, and the last part of this this little subsection of the lecture is about the physical properties of magmas. We had a whole lecture on volatiles, but I think I've summed it up into a couple of slides. So basically, volatiles generally behave as incompatible elements, but they have this special behavior that if they reach a certain concentration or a certain pressure, temperature, some sort of compositional change in the melt, then they can exsolve and make a gas phase. So the volatiles are initially dissolved in the magma, and then they nucleate bubbles. And we can see this on, this is a phase diagram for a water undersaturated melt, in this case some sort of basalt. And if we have 2% water and we just depressurize it, we've not hit water saturation, so all of that 2% water is dissolved in the melt until we hit this curve, and then we basically, the melt composition will then evolve along this saturation line or saturation surface, and at the same time we're producing bubbles. So, you know, the concentration of dissolved water in the melt is going down, but the amount of exsolved or you know, water in bubbles is going up. And so this will often produce vesicles, and then as we'll talk about in the next part of the lecture, these bubbles might be trapped or they can escape, and that will depend on the properties of the magma. Okay. In general, evolved magmas like rhyolites are less dense, and primitive magmas like basalts are more dense. The main reason, or the way you can think about this, is all these ferromagnesium minerals, which are just minerals with iron and magnesium in, olivine, orthoperoxine, kleinperoxine, amphiboles, micas, they're all more dense than a mafic magma. So as we crystallize those minerals and remove them, we're essentially making the melt less and less dense. The important thing here is that these changes are, you know, they're fairly big. Okay, so a rhyolite is maybe 20% less dense than a tholeite. But they're pretty minimal compared to the effect of bubble nucleation. So once you nucleate a bubble, that bubble has a density, depends on the pressure, but it's essentially very, very low. And the net density of a magma that has bubbles in it is much, much lower than a magma that doesn't have any bubbles in it. Okay, silicate melts are made up of these kind of framework-forming cations. So these are cations that sit in tetrahedral sites. Just like in minerals, it's silicon, aluminium generally. And then we also have these framework modifiers. So these are pretty much every other cation: magnesium, iron, calcium. And the more of these framework modifiers that we have, the more broken up the framework made up of silica tetrahedra gets. So up here, this is for liquid silica, so it's just silicon and oxygen, and you can see that it's what we call highly polymerized. There's lots and lots of bonds between the different silica tetrahedra. And these, they're joined by lots of bridging oxygens. And the bridging oxygens are just oxygens that have a bond to two silica cations. As we introduce more of these network modifiers, then we have a mix of bridging oxygens, which connect the two silica tetrahedra. But then we also have these non-bridging oxygens that are not connected to another tetrahedron. So what this means is generally at higher silica contents, we have a more polymerized, more like a framework melt, and this has a low amount of non-bridging oxygens. So that would be more viscous. So something like a rhyolite has this NBO over T, non-bridging oxygen divided by tetrahedra of 0.08, very high viscosity. For the lower silica melts, which have more of these framework modifiers, it's less polymerized, so we have more non-bridging oxygens, these kind of free floating, hanging around oxygens. And something like a tholeiitic basalt might look like this, and it would have NBO over T of about 0.44. On top of this kind of overall compositional control, there's a big effect from temperature. So high temperature melts are less viscous than low temperature melts. And these things kind of work in concert because, you know, a mafic melt is high temperature and low in silica, whereas cooler felsic melts, they're obviously more silica rich, so they have more of a framework, but they're also lower temperature. And so mafic melts tend to have low viscosity, whereas felsic melts tend to have high viscosity. Probably the most important kind of modifier here is that water depolymerizes melt. So when we add water, it reduces the viscosity. So adding water can decrease the viscosity of rhyolitic melts by about 10 orders of magnitude. So this is absolutely massive. You can see here, this is the viscosity. It's a log scale. So going from 0% water to 10% water at about 700 degrees C rhyolite is literally a 10 order of magnitude change. So huge, huge drop in viscosity. The opposite is true. If we degas a rhyolite, then it will suddenly become much more viscous. Crystallization can also increase the viscosity because instead of it just being a melt flowing, it's this kind of mixture of melt and crystals. And the kind of key number to remember is that once we hit about 55% crystals, then it's like the melt kind of locks up. We have all these different crystals bumping against each other and it can't really flow in the same way. We actually get a similar effect for bubble foams, and a melt that is foamy and has lots of bubbles kind of interacting with each other is more viscous than one that doesn't have any bubbles at all.